Perfect. So our next speaker is Markus Brill. Markus, please start.
Great. Yeah, thanks, Fedor, and thanks to all the organizers for inviting me. It's great to be here. And it's also nice within this session to be sandwiched between my old colleagues from Munich, Florian and Felix. So I'm talking about approval-based apportionment, which is a joint work with a couple of people, Paul Gölz from CMU, Dominic Peters, who will speak later in this workshop, but probably still asleep because he's in North America, as far as I know. Ulrike Schmidt-Kreppelin is my PhD student, and Kai Wilker is a former student here at TU Berlin. So most of what I'm talking about is motivated by this idea of proportional representation that I'm sure everybody is familiar with, at least on an intuitive level. So think of a situation where you have some kind of parliament and you have some parties that you need to decide how many seats each party gets based on an election. And then proportional representation, simply speaking, is just this very straightforward idea that if a party gets X% of votes in an election, it should also get roughly X% of seats. Right? It's not exactly X% because there's a rounding issue, but this is the good old apportionment problem that probably most people are familiar with, where we have all these well-known apportionment methods due to Jefferson, Webster, and in Europe they are known as D'Hondt and Saint-Hilaire and so on and so on. So here's a concrete example. Let's say we have 4 parties. And by the way, I should say that in all of my slides, I try to avoid notation as much as possible. So everything will be explained, not everything, but almost everything will be explained by pictures. So that means if anything is unclear, you should just jump in and interrupt me and I'll try to formalize it for you. Okay, so I use colors for parties and have a parliament with a fixed number of seats. I think in this case it's like 100 or something. And then let's say the outcome of the vote looks as follows. So this is like the cake diagram shows us like a third for the first 3 parties. And then of course, naturally, what apportionment method would do is to give 1/3 of the seats to each of those 3 parties and nothing to the yellow party because nobody voted for the yellow party, right? So everybody's familiar with that. And proportionality, a little bit more formally in this example, of apportionment, it could, for example, be formalized by a property that's known as lower quota. And lower quota says that if a party has X% of votes, it gets X% of seats rounded down, right? So that's one natural way of capturing that. Okay, so what I'm going to do now is kind of a thought experiment that's motivated our paper. And the thought experiment is as follows. Imagine you're participating in such a party list election. But now, instead of being required to vote for only a single party, as you usually do, you can now vote for multiple parties. More specifically, we do approval voting over parties. Okay, so you are confronted with an approval ballot that lists all the parties. You can make a cross next to as many parties as you like. You can approve all of them if you like, or none of them. It doesn't make much sense, but you could do it, or any number in between. There's no restriction on the number of parties approved. And then we want to come up with a seat distribution based on this new input, which consists of approval votes over parties. Okay? And just to motivate why this might be useful in some circumstances, let's look again at our electorate and let's imagine that the true preferences of the voters here, and I mean, we have this 1/3, 1/3, 1/3 split among the 3 parties. And maybe the blue voters, they really only like the blue party, but maybe imagine that the people, the 1/3 who voted for red, they also approve yellow. This is what this should indicate here. And the 1/3 of voters who approve the green party, they also approve of yellow. Right, so then basically there is this yellow party that didn't get any votes, but 2/3 of the population, they like it equally much, say, as the party they actually voted for. In this case, and remember this was the apportionment outcome, in this case it seems kind of a violation of proportionality because if you look at the 2/3 of voters, those who voted either red or green, they together make up a 2/3 majority. However, each of those voters is only represented by 1/3 of the committee. So this is kind of the idea that we want to kind of allow approval voting to identify such parties which can lead to more efficient outcomes, right? Because in this case we could give 2/3 of the seats to the yellow party, making each of those 2/3 of voters double as happy as before by not hurting the blue voter down here. So this is the basic idea. So the setting that we are looking at, we call it approval-based apportionment, right? So again, what does it mean? The input, we have a finite set of voters, we have a finite set of parties. Each voter gives us a subset of the parties, approval set over parties. And we also have as an input a number of seats. And based on this input, we want to decide how many seats each of the parties gets. Okay, a couple of words on related work. I think we are the first one to study this setting in general. However, there have been a couple of works who looked at specific rules and extended it to the case of approval voting over parties. In particular, Steve Brahms and his co-authors have looked at a couple of multi-winner approval rules that can also be applied if you elicit approval votes over parties. And there's also some other papers by Javier Mora and Svante Jansson about rules by Fragment and Thiele, where they also consider this option that approval votes can be expressed over parties. And quite interestingly, there's also a quite recent paper in which two Italian authors proposed to use kind of one specific party approval rule for the Italian parliament. They were motivated by the fact that in Italy they tend to have lots of small parties, and it's hard to form a governing coalition. So their idea was to elicit approval votes and then aggregate them in such a way that there's a small number of parties with lots of seats, such that forming a coalition becomes easier. And in honor of the new European champion, I will refer to this rule as the Italian rule in this talk. In the paper, we call it majoritarian rule. Okay, so what we're doing in this paper is metaphorically could be depicted as follows. So we look at this kind of new setting of approval-based apportionment, and we try to see which, we do an axiomatic study. We look at established axioms and see which of those axioms can be satisfied in this setting. And in order to do that, it is very helpful to position this new setting with respect to more established settings. And we do this by the following two inclusions. So the first one should be easy to see. It's easy to see that our setting is a generalization of the standard apportionment setting, where the standard apportionment setting simply consists in every voter voting for a single party. Right now we have approval votes over parties. It's clearly a generalization, or said the other way around, if we restrict every voter to approve only of a single party, we're back in the restricted setting of apportionment. Right, so that should be pretty straightforward. What's maybe a bit more interesting is the other inclusion, namely one can show that our setting can actually be considered a subsetting or a subdomain of the general setting of approval-based multi-winner elections. And this is a setting that has been studied a lot in recent years, specifically in the computational social choice literature. So let me say a couple of words about that, about this inclusion. So the multi-winner election setting with approval votes has a finite set of candidates, a finite set of voters. And then for each voter, you have a subset of candidates, which are the approval candidates. Right? So the difference here is that approvals are expressed on the level of candidates, not on the level of parties. There do not even have to exist any parties in this setting. This is very general, very abstract. So how can we now position approval-based apportionment as a subdomain of this setting? Well, if you put this into a figure, right? So in the general setting, we simply have some arbitrary set of candidates without any structure, and approval sets can be arbitrary subsets of this set of candidates. Right? So an approval set, for example, could, I don't know, I could approve those two candidates, or maybe those four, or those three, and these approval sets can be arbitrarily overlapping. There is no restriction whatsoever. Now, in order to tell you how the restricted domain looks like, let's imagine that, let me define the domain by saying that the domain consists of all preference profiles in which this set of candidates can be partitioned in blocks that are here color-coded. These blocks, of course, will then correspond to parties. And the approval sets are then in such a way that every voter approves exactly a subset of those parties, right? So the set of candidates consists of those blocks here, color coded. And if I'm a voter, then my approval set has to follow the rules that if I approve one red candidate, say, then I have to approve all of them, right? So this would be a valid approval set, for example, but I can also approve more than one party. So for example, I can also approve the Green Party and the Black Party. Okay, so this is this shows you that the approval-based apportionment settings actually can be seen as a restricted domain of the multi-winner election setting, which is useful insofar as now we can import axioms and also voting rules from this more general setting and directly apply them into our setting. Right? And how would this work? Well, we would, given an approval-based apportionment instance, we would translate it into such an multi-winner instance with this artificial candidates for every party. We would just check what the multi-winner rule would output, like how many red candidates, how many blue candidates, and so on it would choose. And this would, from this, we can directly read off the seat assignment to the parties in our setting. Okay, and this explains this other inclusion here. So we have kind of nicely sandwiched our setting between two established settings. On the one side, apportionment, which is more restrictive. On the other side, approval-based multi-winner elections, which is more general. And we will, in our quest to find new axiomatic results, we will actually make use of both these inclusions. So what I've just said already is just by this inclusion here, we can use rules and axioms from the multi-winner election literature and directly apply them to our setting. And doing that, we get results for free. For example, we know that there is a multi-winner election rule which satisfies an axiom known as extended justified representation, or EJR, that of course also holds in our restricted domain. So let me tell you what EJR is. So this is the definition. So it is kind of a negative definition. It says what is not allowed to happen. The following situation is not allowed to happen. It should not happen that we can find a set of agents who constitute X% of the electorate, who are cohesive in the sense that there's at least one party they all approve in common. So there is some way of making them all happy at the same time by one party. But nevertheless, each of those voters approves less than X% of the seats in the committee. Okay, so basically this is saying that if we have a group of that size here and that can be made happy together, then they should be made happy. So at least one voter should be happy. And if this is not the case, then we have a violation of EJR. Okay, so this is a well-studied axiom in this approval-based multi-winner world. And in particular, there are rules which are known to satisfy EJR. Probably the most famous one is proportional approval voting, which I will talk about here. Proportional approval voting was already defined at the end of the 19th century by the Danish mathematician Thorvald Thiele. Here's the definition. It's basically a rule that optimizes some objective function globally. And what is this objective function? This objective function is the sum over all the agents. And what this function looks at is the number of seats that are approved by the agent. So we look at each agent, we look at how many seats does this agent approve, like how many seats are given to a party that is approved by that agent. And then we give a score depending on that number. Right? And the scores is actually this funny harmonic sum here. So what that means is that if the voter approves only of a single seat in the parliament, then he has an H value of 1. If the voter approves of 2 seats in the parliament, his H value, his happiness or his utility, if you want, is 1 plus 1/2. If he approves of 3, it would be 1 plus 1/2 plus 1/3 and so on. Okay, so the idea is that we have diminishing marginal returns of being represented more and more. So if somebody is already represented a couple of times, representing this voter more is less important to the rule than representing some other voters who are not represented yet or have less representation yet. Okay, so that's the intuition behind the rule. And it has been shown a while ago that this rule actually satisfies this or guarantees this axiom of EGR, meaning that it always outputs a committee, a parliament that satisfies this EGR axiom. Okay, so this is nice, and this holds even in the general setting of approval-based multi-winner elections. So in particular, this holds for our setting. Okay, so this is something that we didn't really have to do anything, just the embedding. So this is something we got for free. But of course, we wanted to also to have to get some axiomatic results that are stronger than those in the more general setting, right? So why else would this subdomain be interesting? And the first new result that we obtained is the following. Namely, we were interested whether this EGR property that I just explained is compatible with house monotonicity. So house monotonicity is a very natural notion from the apportionment literature that says that if the house size increases, then no party should lose a seat. Right? In other words, the so-called Alabama paradox should not occur. So I think this is very well motivated in the standard apportionment literature and equally well in the approval-based apportionment literature, because also here we give seats to parties. And what's interesting is that in this general setting, it is not known whether these two properties are compatible or not. However, we managed to show that they are by explicitly constructing a rule. And in order to construct this rule, we now use this other embedding here. Namely, we take an instance of our approval-based apportionment setting. We project it down in a way that I will explain to an apportionment instance, and then apply one of the standard apportionment methods to get a seat distribution. Okay. In a little bit more detail, how does this look like? So this so-called two-step approach consists of first taking as input our approval-based apportionment profile, and then transforming it into a kind of cake diagram, a vote distribution, percentages for each party, and then applying, and then this is the natural input for an apportionment method like Jefferson and others, which we then apply in the second step. This first step is in the literature sometimes referred to as portioning, and is already by itself very interesting. In particular, there's at least two papers by Anna and Abe and others where they study different portioning methods. And naturally, we looked at these works in order to identify portioning methods that might be useful for us in our two-step approach. So in particular, some of the rules we looked at are random priority, there's the conditional utilitarian rule, and there's also the Nash welfare rule. So there's lots of nice rules which in this portioning setting satisfy nice properties, some of them even nice proportionality properties. It was kind of natural to look at those rules and plug them into the first step, and then combine it with a nice apportionment rule. There's not so much variety. I mean, there is variety, but here in our setting, it's usually sufficient if we plug in just the good old Jefferson rule. And then we were looking at whether any combination of those two steps would give us a nice result in the sense that the rule as a whole, the two-step procedure rule as a whole, satisfies EGR and house monotonicity. And it came to somewhat of a surprise to us that this was not the case. So for each of those nice rules here, if combined with Jefferson, we find some counterexample. So this was kind of disappointing. But then even more surprising was that if you plug in another rule, which by itself doesn't seem to be super sophisticated, this rule works. And the rule I'm talking about is this Italian rule I talked about in the beginning. So this Italian portioning rule, let me tell you a little bit what it does. So you might remember that the motivation for this Italian rule was to avoid fragmentation of parliament. So you want to consolidate as much as possible the votes of the voters into a few big parties. And the way this does is in a greedy way. So basically, you first look at the party with the most approvals. So in this example, it's very simple, but let's go to the example. In this example, the yellow party would get 2 approvals, so would be the approval winner. And then all the voters who approve of the yellow party, among others, are assigned to this party. So basically, the first 2 voters would vote completely for the yellow party. The last voter votes for blue because it's the only one that approves. And then we would get this vote distribution and the corresponding parliament. Right? And if you remember from the beginning, that this is basically what we want, because those 2 voters who together make up 2/3 of the parliament are also represented by a fraction of 2/3 of the seats. Okay, so this was a bit unintuitive maybe, but this interesting Italian portioning rule combined with Jefferson gives us some nice rule, and other more natural candidates don't give us such a nice rule in the two-step way. Okay, and this rule satisfies EGR and house monotonicity, but house monotonicity just follows from the property from house monotonicity of Jefferson. Okay, so this is the first kind of new result that we have going via apportionment here. And the other last result I want to talk about is talks about a strengthening of EGR, an even stronger proportionality notion, which is known as core stability. And similarly to this combination here, it is not known in the more general setting of multi-winner elections whether core stability is satisfiable given by itself, not in combination with any other axiom. So we don't know whether the core is always non-empty or not. This is a kind of a well-known open problem in the field. In our subdomain of approval-based apportionment, we were able to show that the core is always non-empty, and we also have a rule that always chooses from the core. So let me explain how we did that, but before I do that, let me motivate why we would even need something stronger than EGR. So why do we need to strengthen EGR to core stability? And the reason is kind of illustrated in this simple example. So in this example, we have 6 voters with those approval ballots, and we have 6 seats. So 6 voters, 6 seats is easy because it just means that every voter intuitively needs to be represented by 1 seat. And if you look at this, this seat distribution here, it doesn't seem very fair, right? Because if you, for example, look at the last 2 voters, so they make up 1/3 of the electorate, but they get half of the seats because half of the seats are blue, and nobody else likes blue other than those 2 voters. And so they seem to be overrepresented. And on the other hand, the remaining 4 voters who approve some combination of red, green, and yellow, they make up 2/3 and they only get half the seats each. Right? So this is not really, doesn't seem proportional if you look at it. Nevertheless, it does not constitute a violation of EGR. And the reason for that is that if you look at these 4 voters, there is no party they all approve in common. And therefore, EGR has no bite in this example. And this is the motivation for looking at stronger axioms. And one axiom that is well studied in literature is core stability, that does away with this kind of common party approach. And it forbids the following kinds of situation. So I mean, this is basically an adaptation of the standard notion of core stability that I'm sure most of you are familiar with, but let me just spell it out what it means in our setting. It means that it should not be the case that we find a set of agents which constitutes X% of the electorate. Remember, if you're X% of the electorate, then you deserve to be represented by that many seats, X% of the seats rounded down. And what should not be the case in order to achieve core stability is that we find such a set of agents that can come up with a hypothetical assignment of the number of seats that corresponds to their size in such a way that each agent in this group is strictly happier with this smaller smaller assignment than they are with the actual assignment. Okay, so the intuition is that it should not be the case that there is a subset of agents who could run away, do their own thing, come up with a smaller parliament, and still do it in such a way that every single one of those agents is strictly more happy, strictly more often represented in this small parliament than they were in the original parliament we started out with. Okay, so this is core stability. And in this example, it actually captures exactly what we wanted to capture, because if you look at these 4 first agents here, they are big enough to be represented 4 seats. So they could build their own committee with 4 seats. And they can in fact do it in such a way that they all like it better. Namely, if they give 2 of these 4 seats to red and 2 of these 4 seats to green, then each of the 4 has improved their happiness. Right? So if you probably don't remember, but the old happiness of the first voter was 1, now it's 2 because there's 2 seats going to red. Similarly for the second, the third voter had a happiness of 3.
Markus has disappeared, but let's wait for him a little bit. I hope.
Hi, I'm back. When did I lose you?
Great.
Sorry about that. Can you hear me?
You just explained the core.
Okay, cool. Yeah, let me start screen sharing again. I'm very sorry about that. Normally my internet connection is stable. I'm not sure what happened. Okay, this is what you saw, hopefully. More or less. Yes. Okay, I'll almost at the end anyway. So this slide was explaining a core deviation for this particular example, motivating that the core actually captures of what we intuitively understand as proportionality, at least in this one example. So core stability is a higher requirement than EJR. And what we have shown in this paper, and it's probably the main result of the paper, is that Thiele's rule, proportional approval voting, in our setting actually guarantees core stability. So if you apply proportional approval voting, the result will always be core stable. Corollary, of course, is that the core is never empty in our setting. This is not known for the general setting of multi-winner elections. In particular, it is known that PAF does not always choose from the core, and it is not known whether the core always exists, or it could be empty sometimes. Okay, that's an open question. For the computer scientists among us who might be worried about computational complexity, so proportional approval voting is intractable, is not efficiently computable. However, we also showed that there's a polynomial time variant of PAF that also chooses core stable outcomes. So a core stable outcome always exists and can be found in polynomial time. Okay, so this is basically the end. So here's again an overview of what we did, right? So we have our new setting of approval-based apportionment, which is sandwiched between these two other settings, and we use those inclusions in both ways. We use the inclusion of apportionment of defining this two-step procedure, which gives us a method that satisfies EJR together with house monotonicity. And we use this rule from this world of multi-winner elections, which in our setting satisfies a very strong proportionality property, namely core stability. So what should we take away from this talk? So, I mean, I phrased everything here in terms of political parties. It could be a possible use case. I'm not directly advocating it. It just was kind of convenient to talk about parties, and I think it's a worthwhile thought experiment in this realm. But there's possibly there's surely other applications that are interesting, since it's just such a mathematically elegant setting. We have shown that in this setting, strong axioms are attainable that are at least not known to be attainable in the more general, well-studied setting. And yes, so applications are probably not limited to politics. And that's the end of my talk, and I'm looking forward to a question. Thank you, and sorry again for the interruption.
Thank you, Markus. I have one short question. This PAV rule seems to be so similar to the Nash product, right? Because if you look at these harmonic sums, they look like logarithm in the limit. And so I wonder if the Nash product rule also has all these nice properties that PAV does.
Yeah, that's a good question and a good observation, right? So it seems to be like a discrete variant of the Nash product rule. The answer is that maybe somewhat surprisingly, the Nash product rule does not have the same nice properties, and the reason is, let's maybe first clarify what are nice properties. So we're talking about EJR here, which was this property I talked the most about.
I thought about core stability.
Right, okay, yeah. So core stability is even stronger than that, but it is actually known that the Nash rule violates even the weaker version of EJR. Oh no, am I losing you again?
We do hear you.
Okay, good.
It
So,
works well.
Okay, good. You froze a little bit. Right. So the Nash rule does not violate causability. Sorry, it violates causability. It violates even the weaker property of EJR, and this is due to a characterization of this earlier paper that I mentioned by Aziz and others, where you can actually characterize uniquely the vector of weights that is used in the rule in order to achieve EJR, and it's known that you have to use exactly that weight vector. And you can think about that Nash falls also in this class. It uses slightly different weights because it's not as discrete, and so it does not satisfy these nice proportionality properties. But it's kind of it's very similar to it. I agree with that. And so one way to interpreting it is that this path rule by Thiele, which is also older, right? It's kind of it's like the correct discretization of the Nash idea. That's one of seeing it.
Very exciting. Thank you, Markus. Yeah, sure.
Can I have a quick question about the core? When you in your result, when you prove core stability, do you need to have this version of the core where a coalition must to strictly improve all of its members' utility, or can you do with the more demanding version where the coalition only improves at least strictly one and leaves the other at least as good?
Yeah, I'm pretty sure we need the version where everybody strictly improves. And I think, but I need to verify this, I think we know that if we look at the stricter version, that this is not satisfiable even in our subdomain.
Okay. So it may be that stricter version is even impossible. Could be. Exactly,
yeah. I think that's, I mean, and that might be known. I mean, maybe not in published work, but I'm pretty sure we looked at this at some point. And it's a good point. I will look it up. Thank you.
Thank you.
We have some time for more questions, maybe from our online participants. We have one offline question.
Hello, can you hear me?
Yes.
When we're talking about some complicated decision-making rules like this one, do we actually have any idea how the voters should strategize? So if I have a preference over political parties or over policies they're going to make, is it hard for me to determine where I should draw the line optimally, whom to approve and whom not to approve? So we know it shouldn't be strategy proof, right? So, but is it hard for voters to understand that, especially if we are thinking about using something like that for real elections?
Right. Yeah, that's a good point. My connection broke in between, but I think I got most of your question. So your question was about like voters drawing the line and strategizing. I mean, I totally agree that this is a valid concern, and I would say it really depends on the setting in which you're using it, right? So I agree that in politics, maybe, I mean, you might have your favorite party, right? And then why should you approve anything beyond that party? But I think there are some cases where it might be useful. So for example, if you remember correctly, the last European elections for the European Parliament, which were a couple of years ago, had like the super long list of more than 40 parties. Like the ballot was more than 1 meter long. And there were at least 3 parties which are about animal rights. So, and then one, if you're like a person who cares a lot about animal rights, right, and you would, in the current system, you would have to choose one of those parties and hope that one of them collects enough votes to go over the hurdle of, I don't know what it was, like 3% or something, or maybe only to deserve even 1 seat, but for the small parties, that's the biggest hurdle. And so in this approval world, the thought experiment, you could just approve all 3 of them, and then you could kind of trust the method that it would coordinate the votes in such a way that if there is enough approval votes for them together, then they will be consolidated in one of those parties to gain that one seat. Right? So I can see that there are some use cases where it's kind of very natural to use it, but I also think that in other use cases it's not so clear, and this strategic decision that you mentioned is certainly not so easy often. And it's also true that none of those rules are strategy proof. In fact, that there's actually a very natural thing to manipulate, which is basically kind of approving fewer parties. Well, it's more natural in the candidate world, but in the party setting, we correspond to approving fewer parties to concentrate your votes on those that you like most.
Markus, there is one more question from Alex Nesterov.
Yes, thanks. So you actually started answering it. I was wondering about the incentives of parties to merge or to split, and whether this has been studied. And it looks under the rules you presented, they look like being indifferent. Is this so or not?
It's a good question. I think it depends on the rule. So there's certainly work on that in the standard apportionment setting. I know that Alexander Karpov has a paper on that, which is about the dot method, where it actually can be beneficial to merge. And so specifically for the rules that we use, it is two-step procedure, which use the Jefferson or D'Hondt method as the second step. We will have the same incentives. So that's for the two-step procedure. For proportional approval voting, we didn't really think about it, so it might be interesting to look at. But I would imagine that it also here it might make sense, because merging might have the effect that two parties who would not get a seat, if they merge, they get a seat together, or they get one additional seat, and then this would be to the mutual benefit of the voters of those parties. But good question, thank you.
Thank you, Markus.